हेलो दोस्तों, आज की क्लास में ऑसिलेशन चैप्टर से एक बहुत प्यारा आर्टिकल सिंपल पेंडुलम हम कवर करेंगे। वी विल बी प्रूविंग that oscillations of a simple pendulum are simple harmonic motion, and after the proof of this SHM we will be finding the expression for the time period as well as frequency for the oscillations। तो करते हैं स्टार्ट। This is our pendulum. The mass which is hanging at the bottom of the string, that is called bob, is m. This L is the length of the string, and I have given some displacement to the mass. So presently the mass is at this particular position. Theta is the angular displacement and x is the linear displacement. So there are two forces which are acting on the bob. One is its weight, and as the string is tightened, जो आपके पास धागा होगा, string होगा, वो खींचा हुआ होगा, so there will be tension also. So two forces are acting here. One is tension and another is weight. So let us mark these forces in our diagram. So tension will be acting in this direction. This is T tension, because wherever the string is connected, tension will be in the opposite direction. And weight is always acting in the downward direction. So this is our weight, mg. So let me extend this line. What will be this angle? From the geometry of this figure, if you will see, this angle is theta, then this angle will also be theta. This is one line, it is L, and parallel to this there is mg, and this line will be intersecting these two parallel lines. So this is theta, that is the corresponding angle. Now just resolve mg into two components. One component will be this and another component will be this. Rectangular resolution of the force. So this component will be mg cos theta, because angle के साथ वाला जो component होता है वो cos component होता है, और this will be mg sin theta. If you will observe the motion in the direction of mg cos theta and tension, so there will be no motion of the bob taking place in the direction of mg cos theta or in the direction of tension. It means they both will be balancing each other. So T will be equal to mg cos theta. Whenever the oscillations are going there, then definitely there is some restoring force. So here mg sin theta will be providing as the restoring force. So restoring force F is equal to mg sin theta. If angles are small, जब एंगल स्मॉल होते हैं तो हमें पता है कि साइन थीटा नियर बाय किसके इक्वल हो जाता है, थीटा के. सो दिस force will become F is equal to mg, and in spite of this sin theta we will be getting theta. Let me mark this as equation number 1. Now from the geometry of the figure we can say that this x is an arc, so we will be using the simple formula arc length is equal to radius into theta. So if you will be observing in the figure, this is your arc having the arc length of x. This string length will become radius of this arc, that is radius, and this is theta. So what will be the arc length? Arc length will be x. What will be the radius? It will be L, and what is theta? It is theta. So from here we will be getting the value of the theta is equal to x upon L. Let me mark this equation as 2. So by putting the value of the theta from equation number 2 in equation number 1, so we will be getting F is equal to mg, and in place of theta we will be getting x upon L. If you will be just taking into the consideration the direction, so this restoring force, that is mg sin theta over f, that is toward me, this way direction, and this x is away from me. It means this restoring force f, or we can say that the mg sin theta and x both are in the opposite direction. So if we will be taking the direction into the consideration, so here comes the minus sign. So f is equal to minus mgx upon L, and this negative sign is because of direction. Okay. So if you will see, m is the mass of the bob. So wheresoever the body is there, whatsoever the oscillation is there, mass will be remain same. This L is the length of the string, that will again remain same. So g is the acceleration due to gravity, that is again remains same. So it means restoring force is directly proportional to the single power of the displacement, and it's the very basic definition of the SHM. What is simple harmonic motion? Whenever the restoring force is proportional to the single power of the displacement, we can say our motion is SHM. So as force is directly proportional to the single power of the displacement, so we can say that, therefore we can say that motion is SHM. Right? Let me mark this equation as equation number 3. Now, according to Newton's second law, force is equal to mass into acceleration. Now putting the value of this force in equation number 3, we will be getting ma is equal to minus mgx upon L. From this m to m, it will get cancelled out, and we will be getting acceleration is equal to minus g upon L into x. Let me mark this equation as equation number 4. Now, from differential equation of SHM, we have already covered the differential equation of SHM from differential equation of SHM. We know that second order derivative of the displacement with respect to the time is equal to minus of omega square x, and second order derivative of the displacement is the acceleration. So acceleration is equal to minus of omega square x, and let me mark this as equation number 5. So from equation number 4 and 5, here is a, here is also a, negative is there, x is there. It means omega square is equal to g upon L, and what will be omega? Omega will be equal to g upon L and its under root. And what is omega? Omega is the angular speed, and we know that omega is 2 pi upon t. So we can say that 2 pi upon t is equal to g upon L and its under root. By just taking the reciprocal, अगर हम इसका reciprocal ले लेंगे तो it will become t upon 2 pi and L become on the upper side L upon g and its under root. Now this 2 pi will get on the upper side, so we'll be getting the expression for the time period, that is 2 pi L upon g and its under root. This will be the expression for the time period. And what is frequency? Frequency, we all know that it's reciprocal of the time period, so formula will get inverted. So nu become, this 2 pi will come on the lower side, that is 2 pi, g become on the upper side, L and its under root. So these are the expression for the time period as well as the frequency. And it's very interesting to note that the time period as well as the frequency of the oscillation is not depending upon the mass of the bob. It is in direct relation with the length of the string and in inverse relationship with the acceleration due to gravity. So whatsoever the mass of the body is there will be no effect on the time period as well as on the frequency. It means whether the body is heavy or the body is lighter, the time period will remain same. So I hope this article is clear to you. In case you are having any query, any doubt, you can drop your message, you can drop your query in the comment section. So मिलते हैं जल्दी हमारी next video के अंदर. Till then, take care and goodbye.